And I'll be using the smaller pen size, 1080p, full screen. We've already talked about that so many times. But for this, gluconeogenesis, the process of making glucose, is chemically really similar to glycolysis, but it's not exactly the same thing as glycolysis in reverse. And so I think the best way to kind of study this would be to draw out the process of glycolysis in reverse, and I'm going to mention the kind of steps that we have to overcome, which, as you could imagine, are the irreversible steps of glycolysis. So yeah, if this was glycolysis in reverse, we would be ending with the production of pyruvate and ATP, and the enzyme that made this is an irreversible enzyme, right? The pyruvate kinase was an irreversible reaction, so we have to overcome that reaction. I do not know what happened with my pen there, but yeah, we have to overcome the reaction of ADP and pyruvate kinase, and just for, I guess, fun facts here, the delta G of that reaction there is about negative 17 kilojoules per mole. So obviously we have to put energy into this in order to happen, ATP being one of those sources of energy. And the way that we do this is kind of confusing to me at first, but from a standpoint of oxidation reduction, which is the ultimate source of energy, it kind of makes sense. So what we have to do is we have to first put a carboxyl group onto the pyruvate. And we're going to be using the enzyme known as pyruvate carboxylase, what a wonderful name, and then obviously having a carboxyl group as a reactant. Pyruvate carboxylase and a carboxyl group, but we're being realistic about this, dissolved in the universal solvent. This is going to give us oxaloacetate as the main product that we're really interested in. We're not really interested in ADP in this context. And then the next thing that we have to do to overcome pyruvate kinase, this is all just overcoming the reaction of pyruvate kinase, is we have to react with another enzyme, extremely long name, phosphoenol pyruvate carboxykinase, and the A died. I don't know what happened to the A, but that's the name of the enzyme, and we're going to be using an energy source in this context, though. It's not ATP, but GTP to catalyze our reactions, right? So we've used up 2 energy carriers already just to overcome the pyruvate kinase reaction. For phosphoenol pyruvate carboxykinase, it's a kinase enzyme, so you know what it's going to be doing. It's going to be, in this context, doing what all kinases do. But let's talk briefly about pyruvate kinase for a second. So for a cofactor of it, it uses biotin, and that biotin, in order to do his job, needs to work with acetyl-CoA. So in this context, it's actually biotin that is involved in carrying the CO2 from in this context, just dissolved in water, to placing it on the pyruvate to give us oxaloacetate. And the way that we do this, though, the way that we are able to do that is by activating the CO2. And what I mean by activating CO2, I'm just going to go ahead and put it in parentheses here, we phosphorylate it, so it's carboxyphosphate. They could not have thought of shorter words to describe this stuff. And biotin needs acetyl-CoA in order to catalyze this reaction, right? And so when acetyl-CoA binds, that's obviously going to cause a conformational change in the enzyme. So we say that acetyl-CoA is an allosteric activator. So when acetyl-CoA binds, conformational change enables biotin to do his job, which ultimately results in the conversion from pyruvate to oxaloacetate. Okay, so once we're at oxaloacetate, we use GTP and phosphoenol pyruvate carboxykinase to convert oxaloacetate into phosphoenol pyruvate. All right, so we made phosphoenol pyruvate, CO2, and then GDP. But the only one of these reactions, or only one of the reactants that we're really interested in terms of gluconeogenesis, would be obviously phosphoenol pyruvate. That should look familiar to you, at least to some extent. And then from there, we finally, with the use of pyruvate carboxylase and phosphoenol pyruvate carboxykinase, we have overcome the reaction barrier of ADP and pyruvate kinase with this negative 17 delta G. And so what we've done is we've taken a complicated reaction, we've kind of broken it down into more smaller, energetically favorable reactions. And in doing that, we've been able to get ourselves back to this. And from there, from phosphoenol pyruvate, it's pretty much up until the next big barrier, as you can imagine, just glycolysis in reverse. Just for funs, I hope you can tell me, go away. For funs, I hope you can tell me what the next enzyme and the next reactant it would be to go from phosphoenol pyruvate if we're going glycolysis in reverse. Hopefully you knew that it was water and enolase. And then to phosphoglycerate, which I know I kind of was running out of room here. I don't know why I cannot make that little mouse precursor go away, which reacts in equilibrium through the use of what enzyme? Phosphoglycerate mutase, which is a mutase enzyme. We know what that does. We're essentially going in reverse, right? So this gives us 3-phosphoglycerate. We're going to go from 3-phosphoglycerate to 1,3-BPG through the use of phosphoglycerate kinase to give us 1,3-bis phosphoglycerate. And then the next step, we're going to go from bisphosphoglycerate back to G3P, reacting it with G3P dehydrogenase and then also NADH as this, because we're doing glycolysis in reverse at this point. I have room to fit it down here, but as you know, G3P is reacting in equilibrium with DHAP, dihydroxyacetone phosphate, and it's converted in that process back and forth by the means of the triose phosphate isomerase. But I'm just going to focus it on really both of these, so I'm just going to kind of draw it out here like this, if I can fit it. Getting really sloppy handwriting as the videos progress. But the enzyme that it's going to react with is aldolase. That's nothing new. And then the product of the aldolase reaction is going to be the fructose 1,6-bisphosphate. Fructose 1,6-bisphosphate for short. I'm kind of having to use a lot of abbreviations here because I don't have as much room as I'd like. So the next big obstacle that we have here is to go from fructose 1,6-bisphosphate back to fructose 6-phosphate. And the enzyme that we have to overcome here is phosphofructokinase. I will abbreviate that as PFK, phosphofructokinase, right? The delta G of this reaction has a negative 22 kilojoules per mole. And the way that we overcome this is through the use of water and an enzyme called fructose 1,6-bisphosphatase. I know that got messy there, but it's a bisphosphatase means that it cleaves a phosphate, right? So we're going to be cleaving away a phosphate, and in the process of this, we're going to be converting our fructose 1,6-bisphosphate down to fructose 6-phosphate. And I can't make a note about it, but I'm just going to just say it, that the fructose 1,6-bisphosphatase, I know my handwriting is getting really bad and really cramped in terms of space, but I try to fit all this, essentially 2 videos worth of material into one. The fructose 1,6-bisphosphatase is an allosteric enzyme, as you can imagine, since it's rivaling phosphofructokinase, and it's going to be inhibited by AMP, and it's going to be inhibited by fructose 2,6-bisphosphate, and I think we've talked about that in other contexts as well, so that shouldn't be anything new in this, at least in regards to this. We're doing this to overcome phosphofructokinase, and so once we have fructose 6-phosphate, we're going to just react that in equilibrium with phosphoglucose isomerase. And I'm going to abbreviate phosphoglucose isomerase as PGI, and this is going to give us glucose 6-phosphate. Tried to really make that look like a G. Glucose 6-phosphate, right? And for 90% of the time, 9 out of the 10 tissues, it ends here. We don't want to go further than that in terms of production. The only exception that I can think of to that is would be the liver, right? The liver being something that's a main site of gluconeogenesis. So only in the liver are we going to actually go from glucose 6-phosphate to glucose. And we're going to have to overcome hexokinase, which is another irreversible reaction, right? So we have to obviously use a new enzyme here. So we're going to use going to convert glucose 6-phosphate just into regular old glucose via the action of water, which hopefully you're seeing a pattern here, and then glucose 6-phosphatase, right? So we're going to be cleaving the phosphate off of glucose at the 6-carbon sugar, at the 6' carbon of our glucose, and then we're going to convert that into regular old-fashioned glucose, which is actually quite toxic to our cells, and then it's going to be pumped into the bloodstream. It's kind of the liver only is going to be doing this type of a reaction. And one of the things that you're going to learn about, and I think it's interesting to me because I can't quite explain it from a level of chemistry, is that kinases, generally speaking, when they're involved in putting phosphates on things, use magnesium as a cofactor, but one of the common cofactors used by phosphatases, the process of removing a phosphate, is calcium. Calcium is a cofactor for glucose 6-phosphatase. And I know we're getting messy, but just to reiterate, we're overcoming the action of hexokinase, and hexokinase has a very negative delta G of negative 33 kilojoules per mole. That's why it plays a role not just in this, but in glycogen production. So let's talk about what we just mentioned. All right, so if we were doing glycolysis, we'd be going from glucose to glucose 6-phosphate because of the action of hexokinase. Glucose 6-phosphate would be acting with phosphoglucose isomerase to give us fructose 6-phosphate. Fructose 6-phosphate would be reacting with ATP and phosphofructokinase to give us fructose 1,6-bisphosphate. Fructose 1,6-bisphosphate would be reacting with aldolase to cleave it into 2 3-carbon fragments. One of those would have to react with triose phosphate isomerase to convert us into G3P, so we would have 2 molecules of G3P reacting with G3P dehydrogenase. In this context, I would draw over here NAD+. If that was something that we were really interested in, I'll just go ahead and draw it as a side reaction. I'm not going to circle it as something that we're superbly interested in. And it's going to react with G3P dehydrogenase to give us 1,3-BPG and NADH. Okay, 1,3-BPG would react through the use of phosphoglycerate kinase to give us 3-phosphoglycerate. 3-phosphoglycerate would react with the mutase, which would change it to the second prime carbon instead of the third. And then from 2-phosphoglycerate, it's going to react with enolase to give us phosphoenol pyruvate. Phosphoenol pyruvate would then react with a pyruvate kinase to give us pyruvate and ATP. Now that's glycolysis. If we're going to be talking about gluconeogenesis, though, it is glycolysis in reverse, with the exception of these few irreversible reactions that we have to overcome. So the way that we do that is we use pyruvate carboxylase in ATP to convert pyruvate to oxaloacetate, all right? Thinking in the back of our head the number of carbons that we're dealing with here. And then oxaloacetate is going to react with phosphoenol pyruvate carboxykinase to give us phosphoenol pyruvate, CO2, and GDP. We used a GTP here and we used an ATP here. Okay, then we're going to react phosphoenol pyruvate with enolase again through an equilibrating reactions to give us 2-phosphoglycerate with the mutase to 3-phosphoglycerate with a kinase to 1,3-BPG, and then G3P dehydrogenases to give us G3P, which is going to react in equilibrium with its DHAP through the use of the triose phosphate isomerase, which reacts with aldolase to give us fructose 1,6-bisphosphate. Now we must overcome the phosphofructokinase reaction. So what do? We use a phosphatase, fructose 1,6-bisphosphatase, to cleave a phosphate group off of it, giving us fructose 6-phosphate. Phosphoglucose isomerase converts it back to glucose 6-phosphate, and 9 times out of 10 we're done there. And then we have just one last step that happens in the liver where we will actually cleave that last phosphate group off of our glucose to convert it into regular old boring glucose.